Hello, and welcome to Lecture 8 of Computational Neuroscience. Today we're dealing with unsupervised learning and reinforcement learning in artificial neural networks. In the overall layout of the course, we're dealing with systems of neurons that accomplish some task or represent data in some way. To date, we've talked about perceptrons, regression, backpropagation, and convolutional neural networks and deep networks. And we've sort of built up on first learning that we can learn functions with perceptrons and regression. And then through backprop, we've learned that we can learn features that describe the data. And through deep and convolutional neural networks, we've learned about extracting abstract concepts from the data. However, all of this work was in service of making the network match some desired output. That there was a teaching signal that was there to tell us what was right and what was wrong. And you may have noticed, growing up as an organism, that you did not have constant feedback on everything you did and everything you perceived. The data that we see, the things we see in the world don't necessarily belong to one class or category, and if they do belong to classes and category, that those values can change in context. And we don't have a corrective signal or teacher showing us how to understand the world for the millions of examples of input data that you get every day. And this data also is very hard to get. It takes a lot of work and effort to get high-quality, hand-labeled or expert-labeled training data. And so we do have to ask, is that all there is to machine learning? Is it just trying to do things that other people tell us? Well, we might want to try learning without getting explicit feedback, and that is the purpose of what we'll be covering today, is how to train neural networks in techniques where we do not necessarily have expert feedback at all times. One of the ways you can do this is by trying to, instead of using ground truth, you can try and label with respect to predictions, but that's fundamentally the same concept. But then there's also unsupervised learning and reinforcement learning. And unsupervised learning is when you're learning without any teaching signal whatsoever. Just say somebody gives you a hard drive full of images and they're all unlabeled images. We want to be able to do something with large quantities of data that don't have labels. Or we can do reinforcement learning, which is where an agent is trying to learn about the world or an environment by interacting with the environment. And as the result of getting some kind of a reward, a positive reward, a negative reward, or a zero reward after every action, it can learn to behave in such a way that maximizes the long-term return of the agent. So first, we are going to discuss unsupervised learning. Again, all we have is input data, and we want to know what we can do with it. We should recognize that in neurons, at least at the synapse, locally, they can be considered a kind of unsupervised learning. This is the principle of Hebbian learning, which, stated by Hebb in 1949, says, when an axon of cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency, as one of the cells firing B, is increased. And that is to say, if it seems likely that the firing of A and then the later firing of B are correlated, and I'm using the term correlated loosely here, then we should think that the weight that the downstream neuron B gives to the input neuron A should be increased. There might be some relationship. And this gives us the adage that neurons that fire together wire together. And one way we could write this is by having the change in the weight be equal to the learning rate times the activity of the output neuron times the activity of the input neuron. So the more the downstream neuron is firing, and when the input neuron is also firing, the more we should increase the weight. There is a problem with this, however. This is unstable, because as soon as y fires once, and we increase the weight, then we are increasing the effect that x has on y. And that means that it'll be more likely to fire again a second time. And this process will repeat. It's a positive feedback loop, and this weight would increase forever. And that is not feasible, it's not biologically plausible, and it would result in neurons just constantly firing, and that would be undesirable in a network. So we can consider a slightly different learning rule, where instead of just changing the weight without bound, we try and change it towards some target. And this was the concept behind Kohonen networks. And what Kohonen networks are is they take some input, some n-dimensional input, and they try and project it into a lower dimensional subspace. And that subspace is represented by a grid of neurons, a two-dimensional grid of neurons. And we want to find a way to map whatever the input is to some point in this space. So the learning rate that was developed here was instead to change the weight to be closer to the input value. So we want the weight, the difference between the weight input for neuron y and the input xi should be decreased. So if xi causes the neuron to fire, then that weight gets potentiated by the degree that there's a difference between these two quantities. But we wouldn't want to do it necessarily for all the output neurons. They just all end up with the same weights. And that again would not be useful, would not help us discriminate different points in this space. So what instead we can do is just pick the most active neuron. So in this case, in the picture, we see this neuron here, the darkest colored neuron is the most active. And if we apply this kind of learning rule with just the most active neuron firing gets the weight update, then what happens is the neurons become sensitive to different common inputs. And what I mean is that they learn typical inputs that they can use as features. And so this sort of extracts good features that help separate out data that is coming in on the stream. And we can also use this to adjust nearby neurons as well. Instead of just updating the most active neuron, we could say every neuron gets updated proportional to how far the neuron is from the most active neuron. So this neuron here would get a complete weight update. This neuron here would be slightly reduced, this neuron reduced again, and so on as we get further and further away from the most active neuron. And in this way, we can sort of create an embedding of neurons that have similar weights, but not identical, the closer they are together, and allow for greater variation the further they are apart. And what we're seeing here on the right is a figure taken from Nakagama, Saito, and Tanaka in 2000, where they were studying maps of ocular orientation or preferred stimuli in neurons in the visual cortex. And every point we see here in the space represents a neuron, and its color represents its preferred orientation of one of these bar stimuli, and the arrow represents the preferred velocity of the stimuli in that visual field. And so we have four colors that represent the four stimuli: a horizontal bar, one oriented at, say, positive 45 degrees, a vertical bar, one oriented at negative 45 degrees. And then we have the arrows where the length and direction correspond to the speed of motion and the direction of motion of the stimulus through the visual field. And I should say this map represents the most preferred stimuli out of this set. And what we have here on the left is a Kohonen map organization of these visual stimuli, the same kind of visual stimuli, but produced using this unsupervised learning rule. And what we can take away from this is I guess the first thing you might say, if knowing that the image on the left is produced by the self-organizing map, if someone were to tell you that the image on the right were a product of that same algorithm, you wouldn't be terribly surprised. I mean, it is not an implausible product of a self-learning rule. And the other thing we should consider is that we see these transitions across the space, across the cortex. They're sort of smooth transitions in that neurons near each other, this region is yellow, and if you move in this direction, it's still yellow, a little bit more, still yellow. And then eventually, though, you do cross a line. There's a gradual line as the most preferred stimuli changes. We see that there's the smoothness, the local smoothness that we would expect from the self-organizing rule that we see in the Kohonen network on the left. But then there are also sort of these junctions here where we get intersections of many different neurons running up against each other. And we could say what we might observe in this is that this is not necessarily a tiling of the space that you would come with, or you would generate if you were asked to lay out an efficient map of these kinds of features. You might imagine having the colors change along one axis and the preferred stimuli changing along the other. And so this sort of looks like an organization that might occur when there's no top-down structure saying this is the most efficient way to lay out a map for certain values of efficiency. What we're seeing here on the right is an orientation map, which is this is a false color image of a section of cortex in mammal visual cortex, where every point in the space represents the preferred stimuli of the neuron located at that location. And the stimuli are broken down into, they were moving bars that were oriented flat horizontally at a positive 45-degree angle, vertically or at a negative 45-degree angle. And the color in space represents which bar orientation this neuron most responded to. And then you can also see there are all these little arrows on the image. And these arrows correspond to the motion and speed, the direction of motion and the speed of these stimuli through the visual cortex. And so any one point in this map tells us what orientation and velocity of that stimuli a neuron prefers the most. And so what we see is that there's a map, a laying out of neurons that respond to different stimuli in a preferred way that's sort of organized in a lower dimensional subspace, a 2D subspace, not unlike the Kohonen map. What we see on the left is a Kohonen map of the same kind of input stimuli. And what we see is that there are, again, we get the local smoothness that we talked about, that, in any particular neighborhood, if you have a small enough neighborhood, the direction of motion, preferred direction of motion, and the preferred stimuli are mostly the same. But as you go over longer distances, you can have variation. That we see the same pattern here. We select a small neighborhood, the direction of motion, change of preferred direction of motion changes slightly. The color, the preferred orientation, bar orientation, remains similar, but over longer distances we can allow greater variation. And so what we can take from this is that unsupervised learning in this way is a plausible explanation for how cortex organizes itself when it's learning to represent different visual stimuli, and then it can use this map to then make decisions or interpretations, or use it to understand the scene. Or we could imagine many such maps extracting many different features and preferred stimuli. And so this is a way to understand the visual world, or to organize data from the visual world so understanding can be extracted from it without necessarily having a teaching signal coming from the top. This next network we're going to talk about is a Hopfield network. This is still an unsupervised learning algorithm, but it uses a slightly different, or rather we should say it has a clear objective, in that the purpose of Hopfield networks is, given an input stimulus, try and produce the most similar stimulus that the network was trained on. And so this network is defined wholly by the weight matrix W, and it is something that can evolve over time, that because this is the first recurrent network that we have encountered to date, which is to say, instead of having sequences of feed-forward layers like we saw with the multi-layer perceptron or the convolutional neural network, all the neurons in this network influence each other. And so this is a recurrent network. And we see that the other interesting thing is that the weights are symmetric, that the effect that A has on D is equal to the effect that D has on A. And so if we imagine the input pattern +1, -1, -1, +1, Hopfield networks are binary networks where they take on values of either +1 or -1 instead of 1 or 0. If we can imagine that this input was something the network was trained on, then we can see what happens when we corrupt this pattern. Say, well, we'll flip the sign on this last element here, and see if the network gives us back what we learned on, the original pattern. So we take our network, we give it 1, -1, -1, -1, instead of +1 on the previous slide, and we see that through the application of this learning rule, where the input is the function, the threshold function of the product of the previous inputs and the weights, we see that it learns to flip back this element to +1, so we get 1, -1, -1, 1, as before. And this is known as a cleanup network. And this is a way of just storing patterns that you've previously been exposed to, or that the network has previously been exposed to, and correct them, corrupted version of these things to something that existed in the training set. So what we see here is the behavior of a Hopfield network that was trained on 6 patterns, a checkerboard, and then various corruptions of the checkerboard. And then on this bottom gray box, what we're seeing here is the evolution of the state of the neurons as the network executes over time. So here, these graphs here, bar charts, are similarity between one of the inputs, P0 through 0 through 5. And then the y-axis is the similarity between those patterns, between the input and the pattern. So we start with giving a corrupted input, and the orange cells mark where the input pattern differs from the desired pattern, or one of the patterns in the training set. And we see that between the first iteration and the second iteration, this neuron's activity or sign gets flipped, as does this one down here, as does this neuron and this neuron. And this process repeats. And as we progress through iterations of the network, we see that the similarity is increasing between that and some of the stored patterns. We see here that 1 is out in front, but 3 and 4 also have some degree of similarity, but then as time goes, 1 begins to dominate, and we get back the checkerboard again, and we have 100% similarity between this pattern and one of the previously stored patterns. There's also a question in Hopfield networks of capacity, and there are a couple of different ways of training this network, and capacity is the number of patterns you can store in the network without having a risk of collision between two patterns, and that is to say that there are two patterns that are sufficiently similar that it becomes difficult to distinguish between which is the correct pattern. You can use the normal Hebbian rule, which gives you a capacity of n, where n is the dimensionality of the pattern, over 2 log n. Use a pseudo-inverse training rule, not unlike what we did for the regression rule. That will let us store n patterns. And then Storky rule is another training rule which will give us a larger capacity than the normal Heb rule, but not quite as nice as the pseudo-inverse. But the important thing to take away from the Hopfield network is that this is a network whose job with the training paradigm is the inputs should be mapped to reconstructions of that input. And this is an important concept that has led a lot of research in artificial neural networks that has produced a lot of powerful results. Now, the concept of getting a network to reproduce its input as its output, as we'll see, is actually a very powerful concept. And it was using another kind of network called an autoencoder, that is a purely feed-forward network that reproduces its input as its output, that enabled the construction of deep belief networks. And deep belief networks are the first network that broke the bottleneck we've had, or the problem we had with deep learning. And it let us, this was developed by Hinton et al. In 2006, and let them build very deep networks by training each layer as an autoencoder. And there's an input layer, a hidden layer, and an output layer. And so they trained first an autoencoder on the input and produced a hidden representation. They then transformed all the data using that representation, and repeated the process, projecting the space into more and more abstract representations the deeper you get into the network, ultimately arriving at a central location, a central representation, or a latent representation that represents what the network was looking at. And this network was trained on the MNIST handwritten digits, and it learned to map input images into one of 10 neurons, where each neuron more or less corresponded to one of the different digits. But the other advantage of deep belief networks is you could also, because you had built up these series of networks that compressed and expanded data from the source image back to the source image, you could also build the network and drive it backwards. So you could pick one of these points and produce images images of digits out. And this was a very powerful tool that let us build deeper networks just by doing simple pairwise or layer-wise training. So the fundamental concept of an autoencoder is that you have some input that gets encoded into a compressed representation, which I referred to as a latent space. And then there's a decoder that undoes that compression and gives you back the source image out, or approximation of the source image. And so here we see a series of input images that were trained using, or that are transformed using a standard autoencoder. And as you can see, it roughly gets the shape of the numbers down. You know, this is, knowing that this is a 9, you would recognize this is a 9, this is a 5, this is a 5, and so on. Although there was an interesting change in training paradigm called denoising autoencoders, which improved the performance further in that you corrupted the input with noise, and you used it to produce uncorrupted output. So it acted much like the Hopfield network. It acted like a cleanup network, except this is strictly feed-forward. And what you can see here is actually these numbers are a bit sharper. So if we compare this 4 to this 4 here, we see that there's this little light bit of ink here that's sort of closing the top of the 4. That could make it, confused with a 9. Likewise, this 9 is more legible than this reconstructed 9 here. And so we saw improvement by changing the paradigm and forcing the network to overcome some adversity in its input. Now, there is a problem with autoencoders, at least a catch with autoencoders. If we look here on the left, we're seeing a graph of the MNIST 10 digits, handwritten digits, projected into the latent space, the compressed representation of the autoencoder. And if we wanted to generate candidate or imaginary digits, we could just pick a point in this latent space, and the autoencoder will produce, the decoder can produce something out of there. But if you notice, these different colors represented data in the latent space. And if we pick a point here that's in the 1 cluster, and we sort of move in a line towards the 7 cluster, if we pick another point over here in the 7s, we'll get something out that looks like a 7. But if we pick something here in the middle where there isn't a lot of representation, then we can't be sure what we'll get, and we may not get anything reasonable out. And that can be a problem if we're encountering new data that we haven't seen before. So really what we want is something that ensures there's some kind of continuity in this latent space, and that there are smooth transitions between one representation to another. And this is where the variational autoencoder comes in. Instead of having just one compressed representation in the hidden layer, it has two populations. One that represents, that's designed to represent the probability distribution, a normal distribution for each element in the layer with an average mu and a variance or standard deviation sigma. And then when we go to reconstruct the data for the learning step, we sample, instead of just decoding the data, we first sample from this distribution, and then we decode that sampled representation, and we try to make sure that that output is as similar to the input as possible. And by adding this probability distribution here on the sampling, what we're saying is we have some input coming in that defines some kind of a neighborhood, and we want things in that neighborhood, things that are likely to be sampled from the distribution, to be similar to whatever the input is. And here on the left hand, or the right hand rather, diagram, we see the same MNIST digits projected into the latent representation or the compressed representation of the variational autoencoder. And what you can see is that there aren't a lot of big gaps between clusters like we'd see over here in the standard autoencoder. And so as we move along this line in the latent space from a 2 towards a 1, we get something in between that sort of, we get points in between, and they look like something. They look like they are on the transition from a 2 to a 1. And so to affect this, we have to add an additional term to the loss function. So it's not just the sum of squared errors on the pixel values of the output versus the input. We also add this term in here. And what this is trying to ensure is that the probability distribution represented by the hidden layer does not deviate too much from a normal distribution with zero mean and unit variance. This is a term called the KL divergence, and it is added into the loss function in much the same way that the weight regularization term was added into the loss function in the regression stage. And here we see the output is a bunch of the result of a variational autoencoder is that these are outputs taken from sampling different points in the latent space. So one of the two-dimensional latent space. So motion along the x-axis is motion in one part of the latent space, and motion on the y is in the other term. And so what we can see is there's sort of a transition as we move, right? So we start here with a 1, say, and as we move up, it starts to get a little bit, sort of fatter and distends until it becomes a 6. And the 6 continues until it sort of mutates into a 2, and the 2 becomes a 3, and we can just find points. And what we see here is that in any particular neighborhood, you get similar looking results. But as you get further away, you can get more substantial changes in what the point in the latent space represents. And so this was applied by Larson et al. To a very interesting application where they learned faces and they learned characteristics of the faces. This again, I say they learned characteristics. These were not explicitly coded into the network, but they were parts of the latent space that seemed to have different effects. So if you move along one axis, you can take a face and give them blonde hair. Although, as you can see, there's it doesn't always work. So if we want to add eyeglasses to a face, you see this face doesn't have eyeglasses. This face does, as does this one, compared to the source. This face just has what looks to be purely the lenses of sunglasses superimposed in the face, but not the rest of the frame, and really no eyeglasses to speak of here. Likewise, with the blonde hair, the hair area gets lightened, but we're losing a lot of the high-frequency information. So if you look at the individual strands of hair, those are all sort of blurred out. So we see it's learned something, but it's not a realistic or plausible image. And it would be nice to see if we could do something better. And so which is what introduced the generative adversarial network does. This is a network that actually it's two networks that are playing a game with each other. So first we have a network that takes some input in a latent space, and in this case we just feed in random noise, and this outputs an image, a fake image. And to start off, this image probably won't look like anything useful. And then we feed these in along with a set of real images into a network whose sole job is to determine whether the network is real or fake. And these networks take turns, and once the turn for training the discriminator network is done, then the generator network gets a chance to learn, and it attempts to produce images that make the discriminator think it's real. And so they iterate back and forth in this way, each taking turns, trying to get better at their job. And when that technique was used on generating faces, we see that the results are significantly improved compared to just the variational autoencoder alone. Again, if we take the blonde hair axis, we see that the hair color is changed, perhaps with substantial changes in the face compared to this face to that face. But we also preserve a lot of the high-frequency information. We're losing a lot of that blurring. In the eyeglasses case, all the faces do have something approximating glasses on them. And as you can see, this technique represents a substantial improvement in the ability to reconstruct data from some latent representation. Now we're going to talk about reinforcement learning.